With that, I now get the privilege of introducing a friend and colleague. Nick Roy is going to come up. He's going to be leading the next discussion segment. You'll hear from a series of distinguished speakers. So Nick, if you could take the stage and take the microphone away from me.
All right, thank you very much, Eric. So I'm going to, at this point, invite my fellow panelists to join me on the stage, Nancy, Jim, Vikash, and I'm hoping that you will all see...
Leslie is right here.
Leslie's right there. Okay, fantastic. I was hoping I'd see Leslie down there too, but that's all right. Oh, there we go. Okay. Very good. Okay, so as Eric said, my name is Nick Roy. I have the pleasure of being the Director of Systems Engineering inside the Quest, but also as a hobby, I'm also a faculty member in AeroAstro, and I do a lot of work with autonomy and in particular robots that inhabit the world around us and hopefully do intelligent and useful things. And what we're going to do today is talk about the challenges, the questions, the research that we're doing around the issues of intelligence that exists physically in the world, that is able to perceive the world, everything around us, all of us as people, objects, et cetera, space, and then move around and, like I said, do useful things. And this is an interesting time to be talking about this. I mean, it's an interesting time for AI and intelligence, natural and otherwise overall, but in particular, it's an interesting time for me as a roboticist because there's been a lot of progress all of a sudden in the last few years. So this is a handful of videos that I either happen to have or was able to get. The top left, our friends at Boston Dynamics, Mark Raybert, et cetera. All of these videos are publicly available on the web. And the one on the top left, Boston Dynamics released only a couple of days ago. And you see a humanoid robot operating in a factory, very human-like, not just humanoid, but human-like motion, picking up objects, moving them around, putting them in shelves, et cetera. And Boston Dynamics, I think we know, has shown even more remarkable videos than this of robots doing all kinds of things. And there seems to be something that's happening with our mechanisms that are now all of a sudden exhibiting incredibly natural and seemingly intelligent behavior. Bottom left is a video from Zoox, a company that I happen to work with, deploying self-driving cars. You can see them driving around Foster City and Las Vegas and other places, and self-driving cars. Josh mentioned them this morning, and they are increasingly part of the fabric of everyday life. And that feels like it's almost happened overnight in some sense, in that, like, you ask people, when are you going to, people ask me, when are self-driving cars going to be here? And I say, well, they're already here. You can take a Waymo in San Francisco, and they're servicing 100,000 paid rides per week. And under some very difficult circumstances in many cases. San Francisco, if you don't know, is very foggy, and these robots operate in fog. They operate in complicated environments. Some of the most demanding conditions being when a presidential motorcade comes through. And you have to know which rules to obey and which rules to violate in order to get out of the way. Bottom right, we have flying robots. So this is a company that came out of my lab, Skydio, and we have flying robots flying around, inspecting civilian infrastructure. These robots, they come with ground stations where, like, once a week, somebody somewhere, across the country presses a button and the robot takes off and flies around and inspects a wind turbine or a dam or a bridge and is able to identify potential failures. And when I lived in California, I would see the person dangling from the bottom of a big helicopter inspecting the power lines, and this seemed incredibly dangerous. And now we might not need to do that with vehicles like this. And then top right is a video from a lab in Japan where these robots are now solving Rubik's Cubes. And what's super interesting for me is that there's this incredible confluence of both understanding the low-level physics, the robots dexterously manipulating, or the humanoid picking up objects and reacting to the weight, et cetera, along with, like, the high-level understanding of, like, the California Motor Vehicle Code and what it means to drive and when it's okay to, like, cross the double yellow line and when it's not okay to cross a double yellow line. And you might think that we naturally understand how to brake safely in traffic, but if you brake too harsh, you're going to get a rear-ending collision. And all of a sudden, we have these vehicles that seem to do this, except of course, they seem to do it until they can't anymore. And we know that these robots are not like at the level where they are partners to us as humans, and they offer, seemingly tremendous intelligence until they don't. And so this is interesting for us in the quest as to like, how do we get to this level of natural intelligence that exists in the world and has to deal with the diversity of tasks and the diversity of environments. That, for me, more than anything, is what really is the question for physical intelligence, is how do you deal with the diversity of tasks and especially the diversity of environments. So that was a bit of a preamble, but what we're going to try and do today is try and understand what these questions are and what some of our answers might be. And so I just figured, just as Josh framed a lot of the discussion this morning, I thought I would try and frame the discussion the same way. So we had a little bit of back and forth over the last couple of weeks about what really was distinct about physical intelligence and embodied intelligence relative to, say, ChatGPT. And one is that the physical world does seem to impose some kinds of constraints, important constraints, on the kinds of solutions that we might pursue in developing intelligence that is at par with natural intelligence. And so we need to figure out what those constraints are and what they mean for the solutions. But this is not just a responsibility to take on, but it's also an opportunity, and the physical world offers structure as well. So there's a certain reasonableness to the way that the world organizes itself for the most part. People who drive in California come to Boston and say, no, there's no such structure in the world. You people are crazy. But leaving Boston traffic aside, there is a certain amount of structure that we can take advantage of and that helps us here. And then a point that Josh made this morning that I also want to echo is that generalization seems really important, and that the form of the generalization can't just be in more and more data, but actually having sensible world models and sensible mental models that go far beyond the data distribution. And what that means for an embodied intelligence is, I think, a question we can try and answer. So I'm going to stop monologuing at this point and actually, with our fellow panelists here, try and actually get the answer to some of these questions. The Greeks taught us that the first thing you do before actually trying to get answers to these questions, you have to frame the field. And so one of the first things that I think that we need to get a handle on is what exactly is embodied intelligence, and why is this relevant to the quest? And so I thought perhaps I would just call on Vikash. You had, I think, put together a nice slide that tied into things that Jim and Josh said this morning in terms of what exactly do we mean by embodied intelligence?
Yeah, so one capability we might mean, which comes online with very, very young children, is the ability to parse our sensory experience into rich, multi-scale, probabilistic models of the world that capture uncertainty over the visible surfaces of what's out there, how they might feel if we poked them or pushed them, how heavy they are some of them agents? Do they have thoughts? Do they have feelings? Might they move spontaneously? So really, how do we learn rapidly and continually such rich, multi-scale models of the world? And also, what are the processes computationally that are going on inside the organism, which must have very different physics than the processes of deep learning, of tuning parameters of very large transformers that manage to produce these world models and keep them in register even when our sensory data is limited or our attention's distracted. What are those questions?
So you said that the model had physics in it, and when you look at this slide, do you want to give us a sense of like where you think physics might reside? I mean, do we have a detailed physics simulator in our head, or?
Yeah, great question. So what do we mean by words like physics and simulation? So here, speaking personally, I don't mean a veridical model that approximates Newtonian mechanics. Instead, I mean some kind of continuously deformable modeling fabric that can acquire the relationship between what the eyes are seeing and what the body can touch, or in the case of young children, what the tongue and the mouth sense when they put objects in their mouth, what constructs the representations of surfaces and their properties, that somehow is sufficiently in accord with physics that when we use it to take actions, we get more or less the right answers, or at least usefully wrong answers. But whatever that modeling engine is, it can learn how to operate in worlds that don't exist, that have no physical reality. Like, as an adult, we can learn to play computer games, which don't have physics. They do have a world out there. They have, if you like, they accord with some metaphysics of physics, that there's a coherent world that can be learned, but it need not be Newtonian.
So I'm hoping that we'll have discussions like this, but I also want to make sure my fellow panelists and all of you know that, like, at any point, please stick your hand up and wave or interject or something. Yeah, go for it, Nancy.
Yeah, I would motivate this even more simply, and semi-autobiographically. For a few decades, I've been studying perception, mostly vision, and I've thought of that mostly as a process of taking light from the world, getting it into the eyes, and processing it in the brain to figure out what's out there. And that's well and good. I can look out at you guys and I can recognize that there's people here. I can recognize some individuals. I can see the whole space. And it's important for an organism to be informed about what's in front of them. But the thing is that most of the real goal of perception is not just to passively observe, but to inform action, right? And the minute we need to do something in the world, that raises a whole higher bar of what it is we need to perceive, right? So if I want to just do something as basic as pick up an object, or pour something in it, or walk across the room, all of a sudden, all of these new things become relevant. Where I can go, where the door is, what the texture of this cup is that I need to know to pick it up. And what that reveals is that to act in the world, which is, after all, how we pursue our goals as an organism, requires not just knowing what's out there, but understanding the physical structure of the world. And that, to me, is the crux of embodied intelligence.
Leslie, you're looking up.
Okay, good. So yeah, I mean, I'd like to, maybe you can play my movie and I'll talk over it while it's playing. So, right. So we like to talk about robots, and that, that what's great about having a robot is that it can change the world, right? It can actually observe the world and understand it, like Nancy and Vikash just described. But then in service of trying to achieve something in the world, it does this interesting and complicated closed loop interaction. So this silly little example just illustrates what's in the robot's head. So the dark areas are parts of space it hasn't seen yet. It tried to pick something up and found that it couldn't, which helped it update its own world model about what was going on. It thought it could find the thing it was looking for somewhere. It moved that out of the way. It still didn't find it. It moves another thing and so on. So what supports this kind of behavior is, again, a kind of an understanding of the physical world at the level of the robot's kinematics, right? So how can it actually move itself to reach somewhere? At the level of what's going on, what are the objects in the world? What does it remember about what it's already done, like that the thing is stuck to the table, and so on. So the important point about having a model, if the robot only had to do this one thing, I could train a feed-forward neural network to do it, and it would be fast and quick, and it would just do the thing. But this robot can do this thing with different objects and different arrangements, with totally new stuff. If we even changed the kinematics of the robot, it would have to learn a little bit locally, but then it could still solve all the problems. So we really feel like the key to generalization is this idea of learning simple models. And that will be my theme a time or two more in this conversation. Thanks.
So, well, let me ask a question, though. I could imagine an agent sitting in front of like Chrome and like pointing and clicking and like responding to Slack and answering questions on Piazza for students, which would mean I wouldn't have to, which would be very nice. And that somehow feels different to the robot picking up and putting things down. One hypothesis, which I'm stealing from Dan Kodacek, is what's different about the robot here is that there's a notion of like exchanging energy with the world as much as information. Is that different, or am I like overstating the importance of like the power going through the lines, and that actually the agent responding to Piazza questions is actually in the world as much as the robot?
I think the agent responded to Piazza questions is really interesting, right? Because it doesn't understand much about the students on the other end. Like maybe you could train it up pretty well and it would be an LLM, and we could have some conversation later about whether LLMs really feel the person that they're talking to. I think I feel the students that I'm talking to when I'm helping them on Piazza. But you could say there's a world out there, but it's a really different world, and it might be harder to learn the underlying structure. For the physical world, the underlying structure is indeed three-dimensional space, and the a kind of clumpiness of objects, the fact that they tend to hang together as matter and so on. So that's a structural bias that we can take advantage of and get great generalization. It could be that the talking to students on Piazza is a different problem that affords its own kind of underlying biases that you could use for generalization. And then the point is fundamentally that that you need some structure to give you leverage in order to be a general agent in your niche.
Okay, and so that sounds, so a physical agent, all agents presumably are going to benefit from some kind of structure, and the structure and the inductive bias that a physical agent has matches a physical world, and the Piazza agent might just need something different for that. That seems reasonable. Vikash, go for it.
Just one thing I want to add to sort of sharpen the contrast between, let's say, online learning and what I'd call embodied robotics. So digital environments were constructed with symbolic and some engineered symbolic languages, like the code that makes the interface, and evolved natural languages that are communicating, that the students are using to communicate with the chatbot. And those provide enormous constraint and simplification relative to the natural environment. So one key challenge that I think sort of shows up for world modeling that's distinctive in the context of embodied robotics is we're working in unstructured worlds which don't even have large components that come with good symbolic models that were designed for exactly the interactions that we'd like our agents to perform. Instead, somehow, the world models have to emerge. And I think one of the hypotheses that many of us are collaborating around here, like Leslie, with your group building on our perception system, is that it's actually possible to take ideas that are very natural cognitively, that the world decomposes into independently movable objects, a capacity that emerges very early on in human development, and build that into AI systems that do something fundamentally similar.
Nancy, you had a video that I think illustrates this point from the natural intelligence.
So one of the things we've been trying to study with humans is to ask, to what extent do humans actually bother to build these rich models just in everyday rapid action? And so we've been doing these VR experiments where we can put people in VR in front of a tabletop with a bunch of objects on it and give them a simple task, like find the banana or pick up the orange. And so what we're trying to figure out is the degree to which to understand their choices in this rapid, semi-naturalistic task is whether they're really building rich 3D models, including, for example, of the hidden spaces, whether they are reasoning about their uncertainty about what they know and don't know, and whether they're running complex forward simulations, or whether in some cases they may have shortcuts so they don't have to do that full rich modeling of the whole world. And so we're trying to figure out what humans do in this situation by running them on simple tasks like that.
And so Vikash and Leslie have both articulated, like, there's some structure there that needs to match the physical world. And are you starting to see, and maybe I'm running ahead a little bit here, so you can tell me to hold my fire, but I'll ask the question now anyhow. Is like, are you starting to see even a little bit of a signal of what that structure might be from these experiments?
Not yet. We're still putting them together, but this is a way to try to compare human behavior to what robots are doing. Where and this is another case, as like Jim talked about this morning, where the beautiful work that Leslie and Vikash and others are doing are giving us a set of hypotheses about what might be going on in the brain, and then we're going to use those to test human behavior.
And then just while we're on this topic of like what is the embodied intelligence and what this is going to mean for the quest, Vikash, like you in particular have been building, you've made mention already of tools that you are deploying with Leslie in pursuit of these. Do you want to say something about these tools and what they're going to mean for embodied intelligence? And I know you're going to come back to this a couple times, but.
Yeah, sure. So we've been pursuing this question of robust probabilistic world modeling in several domains, inferring the 3D structure of objects in tabletop scenes, inferring the true clean databases underlying very messy data sources like the US Medicare Physicians Registry, or inferring models that forecast microeconomic time series and all kinds of other structured data streams. But in all these areas, the core underlying problem is the same. We have incomplete data. We have some idea that there is a world out there that we're observing incompletely, and we somehow want to stitch together what are the objects, what are their relationships, where are we unsure. So this type of computation, it's very different than training a transformer or deploying it on a GPU, but it affords a kind of analogous opportunity to build unified computing automation, platforms and programming languages that automate the math for this. And so that's one of the things that we've been doing in the Scaling Inference mission to enable other missions all around the Quest, is making it easy to scale models that do this kind of thing that's very unusual from the perspective of neural networks, but quite in line with the longer arc of AI that goes back many decades before the recent activity in neural networks.
One of the things that I know painfully well is just the cost of getting data for real physical systems, and B, how poor quality most of the data is for physical systems. Is this going to help? Is this different? Do you need to do something different?
Yeah, well, I mean, one thing some of you may have seen in the demo session over lunch was a system that can learn in real time on a low-end server GPU with no training models of 3D objects that are required in front of your eyes. So that's a level of data and compute efficiency that's actually between 2 and 3 orders of magnitude better than today's state-of-the-art video transformers. And yet, from the standpoint of natural intelligence, that's got to be only the beginning. You know, the brain can actually produce those representations with maybe 20 watts of power. So I think, you know, we're seeing already some early rapid advances that I think will have some interesting economic consequences, and also hopefully a clearer sense of the value of really looking to reverse engineer how the mind and brain do these tasks.
Okay. All right, so I see, looking at the clock here and realizing we need to pick up the pace a bit. I want to turn attention to, okay, we have tremendously good, I mean, I think they're tremendously good existence proofs of embodied intelligence in the form of people and other animals. And there are gaps between what we can do in silicon and what the natural intelligence does. So Nancy, I'm going to ask you as sort of one of the two representatives. I asked Nancy and then Jim as the two representative people who are like doing the most in terms of measuring what the performance is like, what can the natural intelligence do that you can point at as like, this is something that really we need to understand better and put into the system. So should I go to the next slide?
Sure.
Okay.
Yeah, so one of the things that humans are good at is inferring the 3D structure of an object. And so if I hold up an object like this, you have a good inference about what the shape of the backside of that object is that's currently out of view, right? And so we're interested in how well people do that. And one of the ways that we test that, this is work by Thomas O'Connell and others, is with this task at the upper left, where we present an object and then we give 2 different viewpoints, and one of them matches the object at the top and one doesn't. And what you see here is human data with accuracy on the x-axis, showing that humans, who are all the purple dots there, humans are vastly better at this than your average convolutional neural network that's just trained on ImageNet or something like that. However, if you train convolutional neural networks to pair different views of the same object, then they will generalize to new objects of that class. The trouble is they don't generalize well to new objects of a different class. And so this is an existing gap between humans and current standard convolutional neural networks, is failure to generalize to the 3D shape of novel objects. Also shown on the right there with these completely novel objects to humans, humans still can do the match across different viewpoints substantially better than AI systems, unless they're trained on those very same object classes. And so that's one gap, and I think some of the work that Josh and Vikash and others are doing on kind of generative models of 3D shape will be able to do better than this, but this is a way of defining what one of the gaps is.
And I mean, the natural question I want to ask is it just a question of more data, or is there something like very clearly different going on? Is it like architecturally different, or I'm not, difference in time, sequentiality, data presentation? Like, can we even speculate as to what might be going on? Any of us?
We have a little bit more of a hint in the data you see here, which is the y-axis I didn't talk about. And so we can look at just accuracy. How well do humans do it? How well do the various AI models do it? But we can also ask whether they do it in the same way, at least a little bit, by looking at the pattern of errors across particular trials. And so what you see is that that humans are all similar to each other. They're high up on that y-axis and very different from all of these standard CNNs. And that suggests that these convolutional neural networks just trained on massive amounts of data are not doing this in the same way that humans are yet. And so that's why we think that other classes of models that actually build have a generative system to build the 3D structure may come closer to what humans do.
Okay, so we know it's not just quantitatively different, but qualitatively different, but we don't quite know what the answer is yet, right? And Jim, you've been very quiet, so I'm going to pick on you and say, like, where do you see as the gaps?
Well, so let me just back up a bit to just also connect to embodied intelligence. This notion of moving like energy, I think, is really important. Moving masses is instead of just, now we think about moving information a lot, but remember evolution mostly about survival and reproduction. So this is about mostly moving energy, right? Now, the parts, you need to have some information. But that means that those elements, the kind of core computing elements, as they evolved, we want to study them in animals, they're probably already there. They should already be there, even without things like advanced language. So I think it's an avenue into some of these ideas we believe in world modeling that would show up even in simpler systems. Maybe I'll say more about that later. But even complicated systems like monkeys that I and others study. So it gives you an avenue into the empirical side of things that will also connect to the deep beliefs about internal world models that many of us share for more abstract quantities. So I want to sort of channel that on embodied. But then Nancy made two other important points I want to pick up on. One is that, hey, it was easy to stay in this box of studying perception when you just passively do it, but to engage in the world, that's not going to be enough. It was good for a while, and we did that for a long time, and now this mission is pushing us to push our science into this interactive space, which now has all these other rich challenges and also more difficult to study. And then the third point you said is that we don't know yet where all the gaps are. This is one good example. We don't yet know, we haven't made good measurements of those things, and that's where we are at the moment. Oh, you're showing a slide from us now. So just being able to infer like what we actually know about 3D worlds, like Nancy did the demo with you, showed us, and of course you know all about this. We don't actually know how much you know about those things. We may intuit we know a lot. And it's also known that different brain systems, there are these different streams of visual processing that subserve different effector goals, like moving your arms or moving your eyes versus moving your mouth and telling you like right now, right? So we like to think we have this unified model of the world, but there's much evidence to suggest that we're actually running many internal representations as well. So one of the things our team is working on is trying to get grasp-related estimates of 3D objects. That's what's shown here. How if you were in a natural environment and just picking up objects, we could infer the model that your grasp system has, even if you can't report that system to me. And that's what we're attempting to do there, is we get estimates of that and use that as guidance on systems that are trying to also make their own estimates to find the differences, just like Nancy's reporting, thinking that will be a guide as to where we expect the current AI systems to differ. But then we can converge to systems that are closer aligned to us as the work progresses. But we're far more at the beginning than the end on that trajectory. But there is a huge opportunity here, again, to take engineered systems, maybe not today's AI systems, maybe they're the next ones, that we can then align with these kind of new data that Nancy and others are going to now be engaged in collecting. And that's going to be great for both sides of the field, both the AI side and the brain and cognitive science side, which honestly is at our infancy of sort of understanding how our minds actually do that.
Vikash.
I'm going to just piggyback on that and say, I feel like qualitatively, there's already been really critical interplay between AI engineering and reverse engineering natural intelligence that we've learned qualitatively something about just how much more rapidly organisms appear to be able to acquire information that's relevant for action about their 3D environment. But I think one of the interesting opportunities we have at the Quest is at the next phase, how can we make that learning much more quantitative in much tighter feedback loops between AI engineering and natural intelligence modeling? So, the world has learned it was helpful to have platforms that scale up, data collection from, lots of people thumbs upping and thumbs downing an LLM's output, or, a Tesla self-driving car's, maneuvers, and, training neural nets to better match it. They haven't yet spent nearly as much effort, even maybe 0.1% as much energy, trying to build platforms to scale up rich world modeling with uncertainty and matching the fine-grained quantitative texture of what humans actually infer. So, maybe if we actually measure that a little bit, map that part of the sky of intelligence, we may be able to build more accurate models. Maybe now's the time.
I think there's one important, actually there's a couple important things here. One, Vikash, you said uncertainty, and I think it's been really interesting to watch the progression of the AI community wrestle with uncertainty. Is that uncertainty wasn't a thing like many years ago, and then all of a sudden it became hugely important because we thought that a really good way to train our models was to confer the likelihood that any given feature was actually related to the target concept, and we spent a lot of time doing relative frequency counts, and all of a sudden it became clear like that wasn't a great optimization process, and it was easier just like given a target concept, like just get the best weights you can, forget about how much they correspond to likelihood, and then if you're making decisions, all of a sudden that relative likelihood of an error becomes really, really important. One thing I think that physical embodied intelligence does really, really well is assess risk and get out of the way. One of the things that the self-driving car industry is struggling with is like, how do we actually get our cars to get out of the way of something that's potentially hazardous? And I gave the example of the presidential motorcade, in the beginning of this, but there was a self-driving car company that actually had a car stuck because it could not figure out how to get out of the way, and it did not have an appropriate model of risk. I mean, I'm speculating a little bit when I say it didn't have an appropriate model of risk, but it is the case that human drivers, by and large, again, maybe not in Boston, but they know how to get out of the way of other drivers in urgent situations, and that's a really hard thing for our AI systems to do. Leslie, I don't know if you were waiting patiently to say something. Can I get you to jump in here?
Oh, yeah, I mean, sure. So I guess the theme of this little segment, you were talking about risk, which is really important. And I like to think about that too, right? Because clearly once you have physical robots in the world and you have unfamiliar situations, the whole question of risk and uncertainty is really important. The thing that I was going to maybe bring up next, though, a little bit is the ability to learn from few examples. So we talked about how the fact that maybe, natural systems are already born with a lot of kind of deep understanding of the physical world. Another thing that's a gap between human learning and machine learning at the moment is the ability to learn from few examples. And so one of the things we've been thinking about is trying to say, well, okay, imagine that we had an agent that was already somewhat competent, right? So it already knows something about the physical world. It kind of can understand the world in terms of objects. It knows how to pick things up and put them down. But it's not as infinitely brilliant, and it can't automatically invent new strategies necessarily, not because it doesn't have the underlying understanding, but just because, just like you might not invent tiddlywinks, it just kind of can't think of them. So here's an example. Maybe Nick, you could. Oh, I can't tell if the movie's playing or not.
It was playing. I thought.
Oh, okay, good.
Here we go.
So you can imagine this robot in this picture, right? It would like to pick up the purple block. Somebody told it to or something, but it can't reach it. And so we could demonstrate now to this robot once that it could conceivably pick up something and use the thing it picked up to scoot the block into its reachable workspace and then put the tool back down and pick up the block. And if I showed you a trick like that, or you showed a 10-year-old a trick like that, they would be like, oh, well, a 10-year-old would already know this. So Josh can tell us what age kid might not know this, but could pick it up from one demonstration. It's really interesting to think about. What can you learn from one example? And so what we learn here is that you could do this thing at some kind of reasonably high level of abstraction. And what the robot can extract from one demonstration is the sequence of what we call mode changes, but it's roughly the segments where it changes what objects are in contact with what other objects, including the robot. So it can observe that sequence and divide it up into these pieces. Like I grasp the tool. I use the tool to kind of push another object. I put the tool down and I pick up the object. And then with just a small amount of practice, which includes, for instance, having to learn where to grasp the tool so that it can be used effectively as a hook, allows us to, from basically one high-level example and a little bit of practice, learn a new way of solving a problem. And critically, once we learn this new way of solving a problem, this idea of being able to hook an object and scoot it toward us, we can now use that combinatorially with all the other things we know. right? So what's really crucial about this idea, we talked about generalization, Nick did in his introduction, generalization beyond the training data. So here's an example where now the robot has learned to use a spoon as a hook. It can use a banana as a hook now, and it could use a hook to get another hook. Or it could use a hook in a completely different circumstance to get something to be within reach. And so this idea of using representations that allow us to learn from a small amount of data and to learn a thing that's productively combined with other things it already knows, we think is the key to like major generalization.
Can I just add briefly on that?
Go for it. Yeah, please.
For anybody who's thinking, okay, picking up objects, moving them around, this is pretty mundane stuff. What does this have to do with intelligence? I would just say, just take what Leslie just said. We can scale up. And I think a lot of what we think of as our species' kind of quintessential triumphs of architecture and engineering and science are possibly generalizations of this ability to understand the world enough to build novel tools, to discover new things. So I think it's really at the root of a lot of our grander intellectual achievements.
But at the same time, it's so hard. I'm looking at this thing and thinking like you've got to have like a knowledge of like robots and tools and objects, and is all that built in? And Jim, you observed that like it seems likely we come pre-wired with a bunch of these concepts. Are we as people pre-wired with the notion of tools and grasping, et cetera, or did we learn that? It would be useful to know how, because my experience has been that this is hard because like you enter in all the stuff that you think the robot needs, and it gets like 75% of the way there, and then you realize you forgot something. And it's like, oh, I forgot about like, the canonical thing is like table legs. You always forget to tell the robot to watch out for the table leg as it approaches the table. And so like, and that needs to know about that. I'll program that in, and then it gets like 80% of the way there. Oh, I forgot about like.
Well, wait, Nick.
Yes, ma'am.
Okay, you told me to interject, so I'm interjecting.
Yes, good, excellent.
I mean, I think the table legs are actually not a problem if your perception is good, right? So if you can see the table legs, and then I don't want you, Nick, to put the table legs into the robot's head. I want the robot to like see the table legs and say, oh my goodness, I shouldn't run into them. So it may be that we don't have to build that in.
Yeah, although I chose the table legs purposefully because I'm somebody who chronically slams his own knee into the table legs because I can't see them through the top of the table. And so I actually think that for robots might be a real problem for exactly the reason you said, is that you'd like the robot to have some knowledge of something holding the table up and not to slam itself into it.
Just to engage on where that comes from. A lot of this work on embodied intelligence started decades ago with developmental psychologists who showed that very young infants have rich ideas of objects even when they're out of view. So for example, in one of the classic experiments in developmental psychology, infants, I forget how old, but just like a few months old, were shown an object on a tabletop, and then they're shown a drawbridge moving through that space. And when the drawbridge moved through the space occupied by the object, they looked longer because they were surprised, because they knew the object is still there and objects can't move through each other. And those are the rudiments of some of basic understanding of the physical world present very early.
And I think it's fair to say we haven't really figured out the right way to encode that, at least in my robots. Maybe Leslie has figured out how to encode it. And then, Vikash, do you want to say something about how we actually are going to encode these models in our robots?
Well, sure. So one crucial thing is we're not going to encode it per se. We're going to build systems that have a learnable core on top of which it's easy to acquire a diverse set of world knowledge. So what you're seeing here, it's a version of the demo some of you saw over lunch, which is a video from an iPhone capturing an object and then acquiring 3D models of of a scene, capturing a model of the background and then the independently movable objects in it and keeping them in register as they're moved around. And on the far right, there's a mask showing what parts of the world the system knows it can explain well and what parts of the world it knows it can't. And so for people who've watched, either if you have a Tesla or you've seen the growing genre of Tesla fail videos online, you can see that there's something about its perception system, however impressive, which somehow seems to preclude it accurately comparing its internal representation to the data that's right out there. Now what's going on here is, I think, a very early version of a kind of common sense world modeling engine. Right now, all it's doing is it's trying to infer the superficial surfaces of the visible objects and which ones might be independently movable. But over decades, we saw graphics engines scale up, some of us over our lifetimes, from very low polygon and object count games to much higher resolution, immersive, experiences that actually created the hardware market that grew the GPUs that we're now using to train neural nets. So I'm just pointing out that there's sort of a flow from these very basic tasks in AI through computer systems, both software and hardware platforms, to maybe some of the keys we need of learnable world modeling engines that could then support the kinds of embodied intelligence capabilities we've all been talking about.
Excellent. All right. So I think the next thing I want to turn our attention to, so we've talked a lot about what the gaps are. So let's talk about what we think we might want, or what we think that we have learned from natural intelligence that could then fold back into the our computational models, if nothing else, is a way to validate the models in the way that Jim exactly articulated earlier. So Leslie, I'm going to start with you. I think this is your chance to espouse the vision of the modular architecture.
Okay, good. So when I think about trying to build an intelligent robot, I can't imagine just trying to learn undifferentiated goo that maps the input to the output, although there are people who want to do that, and it's good for some kinds of problems, I think. But from a perspective of intuition and also computer science understanding of algorithms, the clear sense is that it would be good to have some underlying modular decomposition of the robot's brain. And so one of the things that I am most enthusiastic about learning from my colleagues who study brains and minds is what we understand about the modularity of natural systems. And so I'm fascinated to understand that different aspects of mapping and understanding spatial reasoning seem to be separated from the way that we think about objects or the way that we think about other kinds of more abstract problems. And so I just want to say that I'm learning a lot and taking that into account when I think about how to design the internal architecture for my own robot. I mean, another important example, the details of these boxes don't matter, and I'm sure that they don't yet exactly map onto the Nancy's pictures of what the pieces and parts of brains are. But another example of something that's really important is actually the backward connections, right? So it's very common, the computer scientists, we almost always just make one of these things be totally feed forward and say, oh, well, there's perception, and that goes into modeling, and that goes into planning, and out goes the controls. But actually, it seems really critically important, and something that's, I guess, definitely found in brains, that what we're trying to do affects the way that we think about the world and even controls some aspects of how the perception system works. And so things like understanding the modularity and understanding the feedback is an important constraint and inspiration for me when I try to design robot controllers.
Yeah, completely the same for me. And I would even be okay with not necessarily understanding the exact architecture, but just understanding what is the operator that causes this structure to even emerge. Is it a Bayesian hierarchical clustering algorithm, or is it something different? And is it operating with a particular bias or not?
I see. I mean, oh, okay, good. So my intuition, I don't know if that's right, but my intuition is that in my system, what differentiates those regions, in a sense, is what the underlying computational pattern is, right? So for certain kinds of vision processing, convolution or something like that might be a really good underlying computational pattern. For planning, some kind of search algorithm, I think, is a good computational pattern. And so it might be that computational patterns are what is different in the different modules, and that's what makes it good for them to be different, because it would hard to do planning using a convolutional network.
Oh, so I completely agree with that, but I would also want to add to that also the information patterns as well. So something that often goes wrong when we implement architectures like this is that we get the information flow wrong. Either information's missing, abstractions are lossy, or there's redundancy, et cetera. And so actually understanding what's at the interfaces would also be hugely helpful. And in fact, Nancy, I think I'm going to ask you to.
Can I have a question?
Yeah, absolutely.
I have like a million pop-ups here. I'm addicted to pop-ups. Okay, how do I do this? How do I pop them? Okay.
Is it not working? Is it on?
I don't know. Okay, so we've been looking at this in the brain, inspired by Josh Tenenbaum's work. He eventually convinced me that this idea of a physics model in the head wasn't completely ridiculous, and in fact, it's an empirical question. And so, let's look. And so, in contrast, the standard system that Jim has done this seminal work in, along with others on the ventral visual pathway, that kind of purple blob there in the human brain, it's pretty clearly involved in object recognition, and we have decent models of that with convolutional neural networks. But the point is that in addition to that, there seem to be these other systems in the brain, shown here with a kind of green blobs, that we're calling this intuitive physics network. And what we mean by that is we're testing the hypothesis that this is the part of the brain that seems to be involved in building a physical model of the world in front of you. It's early days, but what we've shown so far is that if you show a little video like this and you have to judge the mass of that object, it's relatively heavy because it made a big splash compared to an object that doesn't splash as much. We've shown that this system, you can decode from the system whether you have an unstable configuration of objects like this, where something's about to happen, versus a stable one. We can decode whether objects are in contact, for example, when you put one object inside another compared to when you don't. That's important because when one object contains another, their future fates are connected. We've also shown that that region knows, if you look at a little video like this, where you can see an impending collision, that region of the brain represents the predicted future collision. And so we have some of this kind of information about, we have some evidence that this system is doing things that might be expected if it really is this physical representation of the world. And ongoing work with Vivian Powlin, inspired by a beautiful paper from 20 years ago from Ted Adelson and CSAIL. He proposed that we should care about not just things in the world, like rigid objects shown up here in the upper left, or non-rigid objects like this, but we also care a lot about stuff, like liquids of all different sorts. And so what we seem to be showing in early days is that there's some division of labor between the parts of the brain that are engaged when you look at things versus stuff. And we think this makes sense because the physics of things and stuff are different, and the ways we engage with them are different. And so we'll need to do more to nail this, but I think this is an example of the kinds of ways we can use neuroimaging in humans to discover the modular architecture of systems beyond just pattern recognition and object recognition.
Thank you. Now, but this distinction is lovely because this distinction is important not just for understanding how natural intelligence organizes the world, but also how robots organize the world as well. So this is images and video from my own work where robots also reason about things and stuff. In fact, the self-driving car company I work with, there are actually parallel pipelines that do the thing detection versus the stuff detection. And what's interesting is that the stuff detector is actually far more useful for actually picking trajectories through the world and avoiding collisions in many respects than the things. On the right is a video from a quadrotor flying. This video is shot at an abandoned state hospital in Medfield. And the quadrotor is actually doing semantic segmentation and extracting the stuff in the world and differentiating the roadway versus the grass and the buildings, et cetera. And that proved to be super useful as a signal for navigating. So I think there's some rhyming here between the biology and the silicon, in that we do have, or at least a lot of the vehicles I work with have separate pathways for the things versus stuff, and the stuff matters as much, if not more, than the actual distinct things. What the things matter is telling you what to do a lot of the time, but maybe not necessarily how to do it. So anyway, I just thought this would be a fun video to show. Jim, you've been quiet again. I'm going to call on you to what should we be looking to the biology here for?
Well, maybe some perspective that comes from Nancy's slide again. She sort of said, I don't know, she gives me a lot of credit for some work on so remember just a couple decades ago, there was this part of the brain that's supposed to be involved in object recognition, a series of brain areas, right? And that was what the textbook said, and Nancy's work and others showed that. It was when you started to bring engineered systems that try to actually engage in that problem, then you start to check for alignment, and then you get advances, right? So that story happened. Now we start to tell it like it happened, and like that's going to happen again with these systems that Nancy's pioneering to say, look, here are these other areas now that we see, and Vikash and others are starting to build models of how that could work, and then we'll see alignment at a more detailed level. That's that will play out again to all the benefits that are said on both the AI side and the natural sciences side. So I'm just wanting the audience to have that perspective of how the field is like approaching these things. We're not solving every problem at once, but that cycle is already playing out, and I think will especially play out in this area very richly because it's so core to biology, and there's lots of tools to study that, engages our notions of world models that we think abstract beyond that in the way that Josh and others alluded to this morning. So I think it's going to be quite an exciting space there of activity that we've nucleated here in the Quest.
This is your slide up here, by the way.
Oh, you're talking about, that is basically the history of what the ventral stream work that I just mentioned, which only tells us how the first couple hundred milliseconds of, as Nancy said, estimating what's in this room, but doesn't tell us how to plan or what's going to happen next if I do X, Y, or Z. As Leslie said, convolutional networks that's not good for doing those kind of things, but intelligence relies on our ability to do that as well, not just make an initial estimate, which is out here. Now we have pretty good models of that, and now we can build on that to say now that we have those models, we can go beyond. You saw examples of that from Rebecca this morning, and going beyond in other areas as well. So this is the science scaffolding the next science, and I think we're going to see that in this embodied area, especially. Now that we can make initial estimates, how do we use them to reason about? And that's the challenge that we're going to take on next. We are taking on.
What I think is interesting about this is, so I've just done this like nice song and dance about how like the things and stuff, separate parallel pipelines exist in robots as well, but they don't exist like this. So the dorsal and ventral streams, like I would never do that in a robot. I would want all of them feeding into one unified representation at the end that I make decisions on, rather than having like one pipeline for like the distinct objects, et cetera, and a separate one for like action selection. That's bonkers to me. So, you know.
Pretty interconnected.
Okay,
We like to have
all right.
separate pathways, but there's connections, loads
Okay.
of connections between them.
All right, that makes me feel better, but I'm still super curious about like, you know, how those emerged as like separate pipelines.
Where does it all
related.
come together?
Yeah,
No.
that's right. Go for it.
Well, I think you have my slide up next, which will maybe help us take a view. So one interesting hypothesis that some of us are exploring is what if we look to alternatives to computational patterns or primitives other than convolution as a way of understanding sort of how to build up intelligent world modeling and action planning, which can help to address how information flow from anatomically distinct pathways might be integrated to support, for example, action planning that's informed by things and space and stuff. So an interesting motif that we initially started working with really only on the computer science side was a class of Monte Carlo method that allow you to draw inferences about variables in isolation or in connection, and also kind of weigh or estimate the quality of how good those inferences are. And it turned out, perhaps surprisingly, that you could make a mapping hypothesis between that inference problem and a single cortical microcolumn, maybe, call it, I don't know, order scale a millimeter length vertically in, a 6-week-old mouse, that spatiotemporal scale of mapping. But one of the things we found was that if you look at how columns are connected subcortically, there are pathways which go from what in our theory would be an individual variable back down to a more central region and then back up to the source column they came from, which turns out to be the right information flow for implementing a kind of resampling step, which it turns out is one of the main building blocks of larger scale Monte Carlo algorithms. And so it turns out you can keep following that parallel using modern high throughput neuroanatomical data sets like the Allen Brain Atlas. And we actually found that you can correct errors in some of the data from that data pipeline using our theory. And then that, in turn, gets to an interesting new hypothesis for reading out modularity for the brain. So one of the things we've just started to look at is, under this mapping hypothesis that individual microcolumns are implementing single latent variables in some kind of probabilistic model, well, can we now read out from viral tracing of the connections that are intercolumnar what the dependency structure between the variables in the world model is? So the point I'm trying to make is that for each generation of AI modeling toolkit, we can make explicit mapping hypotheses that are grounded in what we know qualitatively from behavior, but then actually make quantitative predictions about both behavior and neuroanatomy. And right now we're at this incredible moment where 10 years ago, not only do we not have the theory, but we didn't have the data. Now we actually have both the theory and there's a Python library and a great 3D interface that lets us test the models against the data. So I'm much, much more optimistic than I would have thought about the prospect of really fine-grained virtuous cycle spanning AI and natural intelligence.
And I think this is, you're referring to that library here in GenJX?
Yeah, that's right. So here what you're seeing is a probabilistic program written in the scaling inference platform GenJAX, which we've been using for 3D scene perception and natural language understanding. It turns out we can compile a broad class of these probabilistic programs to spiking neural circuits that run on computing elements clocked at 10 hertz, and that give quantitatively accurate predictions for multiple data sets from the Allen Brain Atlas. So it's a sort of very precise version of a mapping hypothesis between an abstraction in silicon and what we think might actually be going on in some region in the brain.
And do you have a sense of like at what level, so there's abstractions at work here. What sense does the base level abstraction not matter? I mean, do we really need spiking neurons at the very bottom level to get these kinds of inference procedures, or is the spiking model just an artifact of like synapses and potassium pumps and things like that?
I'll play that two ways. So we think about the emergence of physics from kind of pre-paradigmatic studies of motion. Right? There's many levels of spatiotemporal precision at which you can try to describe motion. And they eventually, we were able to build theories that were cumulative. They cohered. That is, like mechanics at our scale could be explained by mechanics itself, run on model systems at a much finer scale, which could be eventually explained, or gases could be explained. The macroscopic mechanical properties could be explained by statistical mechanics on the micro scale. Even before you get to quantum or other physical theories. Right? So these multi-scale models cohere. That's a big part of the cumulative success of physics. So what we're exploring here is a set of hypotheses which we think, if they continue to bear out, could be similarly cumulative or analogously cumulative, in that they posit specific spiking mechanisms that have kind of various time-averaged behavior that in many ways accords with what people like Jim and others have argued as most computationally significant at layer 2-3 of the cortex, for example. But they make much more precise predictions about how that behavior arises from a much more microscopic phenomenon. So there are probably some interventions where you don't need the microscale detail. But the more specific the mechanism, in some sense, the stronger the theory, the more interesting empirical tests are possible, at least in principle.
Right.
I would just add to that the theories that Vikash is laying out here are like giving us whole new ideas of like what to look for. That people have had textbooks of descriptions of what these dilemma cortical loops, basal ganglia loops, done for decades, but they haven't considered them in this kind of context now, and I think this is a real chance that there could be serious breakthrough in how we think about those things. The work that Nancy showed on our work, or mentioned on our work, was really just estimating the function spaces of the layer 2-3 neurons to channel Vikash across a series of cortical areas. But those areas are interconnected with all these deeper brains that we don't have a good theory for yet, but this is an avenue that's sort of providing an opportunity there to test this idea. We say, actually, these are what these loops are for at an engineering level. And again, that would be an amazing breakthrough for neuroscience if that turns out to be the case. And we don't yet know that, but we can test it.
But I think you asked the important question, which is what should we be looking for? What should we be building? And I think, Jim, this is your slide.
Well, yeah, so this is echoing the point. I forgot you had the slide of of kind of what the work that's been done so far is like, here's how we make an initial estimate of first 200 milliseconds, what's out there, what is the object, not even the stuff, just the things in this case. Like this is a person or a car, right? And this is kind of, we have some okay models of this and mappings to the brain of this. But then I think, and that sort of led to, as I mentioned this morning, okay, we have decent scientific models now. Those are being used in various ways. As Nancy and Rebecca mentioned, we have deep network AI that sort of grew in crazy ways out of this all over the place, and now is transformers beyond what this was originally motivated by. But now if you go to the next click, I think there's now we're thinking about, okay, as you unfold over time, now you're getting into prediction space. And then as Vikash and others would point out, if you click again, Nick, like you can still make estimates of these things either under very uncertain conditions. Josh showed some of that this morning with the word uncertainty. And yet, if you're playing that, you can still make some decent estimates. That's probably a person walking down the street there. And so that, if you click again, is like as we build models that extend from this initial domain, which are not wrong, they're just approximations of the layer 2-3 hierarchy we think, but that are augmented by sort of full loops and doing sampling and re-estimation, and saying this is actually this is an evolving estimate, if you will. All that's probably happening for us very subconsciously. We're not aware that this is going on yet. Our visual system incorporates these ideas. That's going to lead to even better models of what's happening at either finer grains, perhaps, and then maybe next generation cognitive AI, as Vikash and Josh are channeling as well. So following the same playbook at sort of a higher resolution and more potential AI impact as we extend the time domain into this uncertainty domain here. So that was what this slide is about.
Just something I want to add, what you're seeing on this slide, something I find just really exciting, that because of the interplay between AI and natural intelligence, the way we explore the space of possible tasks has become very, very different. So if we're thinking about, making better vision products, right? Maybe you start with like, a street scene with just, one car and you move to 2 cars. Okay, but if you're instead trying to make something which could see everything a human can see anywhere a human can see it, okay, well, maybe we're not going to try to scale out in coverage just in terms of the number of cars on the road. We're going to have to understand what makes that broad generalizability of robust perception possible. And so, these movies that you see connect multiple labs and platform teams on the Quest to say, okay, let's build infrastructure that you could apply to indoor scenes and road scenes and VR across all the kinds of experiments you've seen us discussing on this panel, and view them in ordinary conditions, but also in these kind of point light visuals where you're seeing just a cloud of dots where the brain can still stitch together a really interesting, coherent perception of space. And maybe all of us have driven at night, we've driven in bad weather. There's lots of really interesting real-world settings that are really consequential for the autonomous driving industry, where there are restrictions on autopilots. But by studying these kinds of, what mechanisms, first, what level of ability do humans have across ordinary and these other viewing conditions, and then having platforms to scale up that process, maybe we could get much more capable vision systems ultimately.
One of the things, so I think there's a couple of things here. One is, I really like the point you're making there, Vikash, about physical intelligence also has graceful degradation mechanisms. So
Yes.
yeah, we wouldn't want to have to act in the world given the signal on the right, but we can. And I think one of the limitations of existing computational models is they basically fall over immediately when presented with data that looks like this. The other thing I want to point out, though, here, which I hadn't realized the first time I looked at the site here, Jim, is that for a robot, those time constants, 200 milliseconds and 2 seconds, are unconscionably long. That's forever. And so, there's an interesting mismatch that I hadn't really noticed before. Is that your self-driving car traveling 75 miles an hour down, the 90 does not have 200 milliseconds to wait for the next percept. And so, and I think we understand that in humans and other species, that a lot of pre-processing happens that allows early action to happen.
Well, and prediction. That's why prediction's important, right? It's too slow to process things online as they come in, right?
That is true, but prediction is really hard and also slow from a computational perspective. And that, in fact, if anything, we're trying to get away from having to do explicit prediction because it's so fraught and noisy and slow.
But I mean, this point you're making, Nick, points out a nice quantitative opportunity for the psychoscope, actually, that we're building at the Quest. You could imagine if you want, so this 200 milliseconds, right, sort of partly that emerged from these very classic studies of, random images that lack spatiotemporal continuity. And so there's this enormous surprise that people could kind of pull out some of the identity of objects from images flashed at just 100 milliseconds or 200 milliseconds that were unrelated. Okay, but Nick's pointing out to drive down the freeway, actually, we need to do processing that's much more predictive, just given the slow speed of biological neurons. So that's a really interesting regime, which again, we at the Quest can study. Anyway, we should talk more about that.
Yeah,
that's interesting.
And it's also the case that reaction speed is clearly learnable. I mean, Formula One drivers have very different reaction times.
And mine's much slower, as it turns out. Yes.
Yeah, mine too. Yes. All right, Nancy, did you want to tell us about?
Oh, well, just a general, what can we learn from brains? I mean, it's more, I will say it's more salient to me what neuroscientists have to learn from AI, because there have just been so many examples of that, from Jim's work to all the other stuff. It's really popping up all over the place. I did not expect this 5 years ago. I was still trying to avoid it 5 years ago, and now I'm just it's so useful all over the place. But I do think, at least at a general level, there are some lessons, maybe, for AI from neuroscience, and that is the most intelligent system we know. That one is highly modular, and so we might think that would be a good way to design AI systems too.
And Vikash, I think this was your slide.
Yeah. So one thing I think it's easy to lose sight of But hopefully these videos all will show. So can you tell me, for this video on the left, what do you see?
Giraffe.
So it's pauses, some people saying giraffe. Okay, and are you sure?
Yeah.
Some people are pretty sure, some people it's like, I don't know, maybe. Okay, yeah. So, there's essentially, and would you say, is it, right now, is the right leg in front of the left leg? We could do this, say now. Yes, okay. Are you sure about that? Okay, so some people are reasonably sure, some people are not so sure, right? So the one interesting thing that this class of image, I think, highlights, you can just imagine as you make the dots sparser and sparser, it gets less and less clear what's going on, but there's still a sense of a percept. Or when you're driving at night, when you see, like I could ask, how many cars are on the road in front of you? Take a little while, right? If I only gave you half a second or a second, maybe you're not sure. Right? So, or if you're, I guess you can't see the video on the right, but it's from a head-mounted camera in a football game. So the point here is just that it's easy to forget that there's just fundamental reasons why human perception has to deal with pervasive uncertainty. We can see in cases where the sensing's limited because of rain and lack of light. We can see in cases where the computation or attention is limited, like in the middle of a football game. And we can also see in these really remarkable edge cases, like these stimuli, which I think were from an alum of Nancy's lab, actually, on the far left, or a collaborator of Nancy's group, which show that we can infer surfaces in really quite unrealistic conditions. So I'm highlighting that because if we really want self-driving systems or AI systems that can build models of the world from data in our phones, or if we want an understanding of how the human visual system works, then I think we're going to need to confront the fact that although much of the time we might think we know what's out there, there's good reason to think pervasively actually we're not so sure, and we need systems that can somehow robustly track that uncertainty.
So these are great, and I think another example is air vehicles often go through high-rate maneuvers, and you have to set yourself up because you know that your perception system is going to be massively degraded during that high-rate maneuver, and you're basically going open loop, which is a very difficult thing for an air vehicle to do. And so you have to align the task with the representation they're using at that time, and I think that's something that we really struggle with. All right, how are we doing on time? Jim says we got 10 minutes. I want to leave a little bit of time at the end for Q&A. So let's just try and bring the slides to a close here by just trying to answer the question. So the quest as a whole, I think, is really trying to develop a new discipline and extract principles that should inform our understanding of the systems in the way I think all three of you have articulated, or four of you, excuse me, Leslie as well, throughout the course of the last hour. Do we have a sense of what are those principles? What are those questions? What are those ideas beyond just measuring phenomena and observing behavior, but what are the ideas? And Leslie, I think that you have a slide here that can start to speak to this discussion.
I see, a little bit, right. So then the question is, what am I really going to do because of what I've learned about brains and so on? And at least one thing is to really think seriously about runtime inference. So one principle that we don't really say much out loud, but fundamentally, for humans, the easy cases are easy. The easy cases are quick. If I ask you an easy math problem, you're fast. And if I ask you a hard one, you're slow. In the prevailing paradigm of a fixed feed-forward neural network, it's this one computation which is going to take just as long to do everything it does as every other thing it does. And that just doesn't seem appropriate, right? So then it turns out after some digging, we find results in theoretical computer science that tell us that actually learning can be more efficient when you're planning to do online computation than when you aren't. And we have some results that say that actually trying to make a circuit that could avoid doing online computation becomes kind of computationally intractable. So a theme of our work, and it's exactly related to this idea of building and using world models, is that we can build systems that solve the easy cases fast, but retain the generality and the generalizability to solve the harder problems, but maybe with more thinking.
I just want to add to that very briefly. So, and for people who are following the sort of shifting investment landscape in LLMs and industry, we're also seeing a very similar recognition.
Yeah.
For, the last several years, the push was make the transformer bigger. But that's actually not what's happening right now. Now we're seeing much more interesting architectures for compute at inference time. And the view from the standpoint of the mind and brain, or indeed most of the history of AI prior to neural nets would be, yes, we have very good fundamental reasons to think that much longer running inference time processes are pervasive and essential and useful, and we just need to figure out how to scale them.
Jim, in terms of ideas or lessons or principles that we should be trying to extract over the next horizon?
Well, again, I'm going to come on, I'm not going to come on the principles. Maybe I have my guesses there. I will say that the reason you're putting this slide up now, and this is a slide from my colleague Mehrdad Jazairi, by the way, this is his work that I'm just advertising. Like, he is showing that we can study in these embodied systems, in this case non-human primates, them doing amazing things. If you didn't see the monkey's arm, you might think it's a human, one of Nancy's humans, doing the find the grape task or getting a goal done. And this is no surprise because these are evolutionary cousins. And why am I telling you this? Because we can study this at the neural hardware to give us insight into the computations. That's, again, what happened in the visual system. And he and others, and I think our group to some extent, but especially his group, are geared up to now do this in an embodied space. And so this isn't just phenomena of the mind and behavior, it's also the neural hardware that's supporting it, and there are tools to do that in this space. Again, this is why this is a really interesting space, embodied, as opposed to something like language, which is also interesting, but it's harder to study at this level, right? So again, we're doing both of these things in the Quest, but this is sort of fundamental to how these systems evolved. And so looking for principles, I think that's a very hard question to answer here, Nick. So I'm not gonna offer my speculation other than we believe in some form of world models. I would say some approximate form of world models, and I think that's a principle of the neuroscientists need to figure out how are those world models implemented in hardware. And again, that is again where I'll point to some of the things Vikash is suggesting, because that is still a not understood thing in brain sciences. We conceptually believe them true, but how they actually implemented, that is still an open question. But I think will lead to big breakthroughs if we can nail that.
Although I will push back on your reluctance to articulate a principle, and I think you did early on, which is, or I think we have collectively, which is certainly for physical intelligence, there seems to be something about the structure and the constraints imposed by the physical world that needs to be matched to the structure of the intelligence as well. Like you asked me to make sure it said, like, what can we learn at the neural level for working with the effector, but I think the end effector itself is really important to this enterprise. Bronowski said that the hand is the cutting edge of the mind, and I think that's really important here, is that our ability to interact with the environment really does give us an advantage in terms of having intelligence and understanding intelligence.
It certainly shapes the demands on the internal compute,
Yeah.
and then how does that internal compute work, and what are those principles? That's what I think both are true, right? So
and does so in a distinctively human way, right? Like most species don't have anything like the kind of fine-grained control we do. It's really one of the distinctive things about humans. Yeah.
And then in terms of the tools that allow us to implement these and make them happen in silicon, Vikash, I think this slide is yours.
Yeah, I'll say, I think one of the things we've all learned is sort of the power of automation that unlocks greater scale compute. That's undeniable, and any approach to engineering AI or reverse engineering natural intelligence needs to be a theory that's built from the beginning with an eye to its economics of scale, not just the physics of scale. And one of the things we've been working on from a computer science perspective is how can we have something that gives the same kinds of automation for calculus, which is what really enabled deep learning. That is, systems that could take code representing a function and calculate its derivative efficiently, and then parallelize that calculation, but extend it to the full interactions of probability, calculus, and symbolic metaprogramming. I say that because the phenomenon of how the mind arises from the brain is a really classic example of a multi-scale probabilistic phenomenon. The systems, behavior is at a much slower time scale than spiking neural activity. So I think one of the enablers for many of the models that we're building at the Quest is automation for this broader set of core math operations and their parallelizability. That's kind of analogous to what TensorFlow and PyTorch and JAX did for enabling the scale in deep learning.
All right, very good. So I think we have time for a couple of questions. Jim has not held up the 0 minutes slide left, so do we have any questions or, hopefully we've posed questions and some idea of the answers that we might have. But if we have questions or thoughts or comments from the audience, I don't. Oh, very good. Yes, please.
Hey, thank you so much for this. This is really, really interesting. It's not often you get people comparing AI and in vivo at the same time and know much about both. So my question is this, based on what you've done over here, and actually since you presented monkeys, I'd like to hear what you have to say about things such as AI passing the Sally Ann test, not just as a pattern recognition thing, but actually passing the Sally Ann test. And also, I don't know if the monkey hand in a jar thing is real, but assuming it is, if a monkey can't do that, whereas your robot can actually use a tool to grab something, whereas a child can very easily drop something in a jar and extract its hand, how would you rate that in terms of an actual living primate not being able to do something as obvious as, hey, if I release this banana, I can escape?
I could say a little bit, but not much. Just first on what the Sally Ann task is, for those of you who haven't heard about it, this is a classic task going back decades, originally from developmental psychology, again, source of many ideas in cognitive science, is the question of when and whether and how young children can represent the contents of another person's belief. And this is a fundamental thing that we humans do, that as far as anybody can tell, no other primate does in anything like the way we do. So for example, we can understand that your belief is different from mine and is different from reality. Your belief is wrong, right? Or your belief is true and different from somebody else's belief. And so that ability is sort of a key thing that humans do. And it was one of the blobs in my brain picture there. That was the work of Rebecca Sachs when she was a PhD student in my lab. She discovered that, astonishingly, there's a small part of the cortex in humans that's selectively engaged just in thinking about what other people are thinking. Quite remarkable. As for where AI systems are with that, I know there's been lots of work with large language models, testing them on versions of the Sally Ann task. And in the early versions, they could do it in narrow domains, and then there's a problem because those tasks are all on the web, and maybe they learn literally the answers. I think the more recent view is that if you test them in a more abstract way where they can't do it just based on memorized text, they're not as good. Maybe Josh knows this better than I do. Are you up on the latest on that? Or is that? More or less, that's right. Okay, good.
But Vikash can probably say something about other models other than LLMs, right?
Right.
Yeah, I will say actually one of the
Which are way better.
the first probabilistic model I worked on when I was a first-year grad student was actually a model of the Sally Ann task.
Okay.
And we now have probabilistic programs that can do much more open-ended inference of goals of human users, and Jim alluded to that earlier in his intro talk this morning. So I think, seeing user interfaces that maintain much richer models of human beliefs and goals and are therefore able to be more responsive to us, that's something that I think is actually a relatively likely, pretty near-term project to come out of what's going on in the Quest. But yeah, you were maybe there's also the monkey.
I didn't really get what that task was, so somebody else.
So my sense is, let me see if I can guess. I don't really know, but I think the idea was there are probably some animals who, once they're holding a desirable thing, don't want to let go of it, even though they should do it for longer horizon reasons. And certainly, I mean, that in robots, that gets to the question of what people call alignment, which is a kind of a weird word, but it means roughly, what are the robot's goals? And so, we set up robots to try to be rational relative to some objective function. So we, the engineers, typically put the objective function in the robot, and then the robot should just be rational with respect to that. So if they won't necessarily, enter these tensions of, I really want this, but I really want the other thing, because technically speaking, they'll want one thing more, and that's just how it's going to come out. Now, there's an interesting, actually, kind of root of both of these questions, I think, which is, as we make a more general robot, right, it's going to go to your house, and it's what it's supposed to do. Its objective function is presumably to do what its human wants it to do. And then it will have this kind of very abstract Sally Ann thing about trying to infer what the human that it's working for wants, and then trying to act in a way that is rational with respect to its own uncertainty about what it's supposed to be doing. But these are the kinds of things that the sorts of models that we're all talking about can actually address.
All right. I think I see Al pointing. Oh, please. Last question. All right.
Thank you. We seem to talk about biology and computer science, but for example, Penrose and probably most of you guys think that consciousness is actually quantic, right? So, and when you say probabilistic, it seems to be in the direction of the model that could explain mind. I don't know if you have some thoughts about, or are we missing physics in this room? We need to put the physics department of quantum computing physics around the other building, or something that you show in the later on.
I'll say something about that. Well, I think one of the most interesting roots of the quest is really in what are the possibilities for articulating and testing various kinds of materialist theories. First, for intelligence. Second, for some of the contents of consciousness, which are produced maybe by intelligence, speaking a little bit loosely. And then we can get to this very mysterious question of, the C word itself. Okay, so one very important class of materialist theories would be that spiking activity of a certain kind produces most of, let's say, intelligence. That may not be true, but that's a kind of materialist theory which we could make objectively testable by building platforms for behavioral data collection and simulation. Personally, I think that's likely to be really fertile ground for quite some time. There's so much room for us to explain the phenomenology of the brain and how it relates to intelligence and get a clearer read on what is the residue. What might the residue be, even in principle, before trying to invoke other scales of physics, which may not be necessary. That's my own view.
And I think your reference to Penrose kind of matches the question I think I asked Jim or Vikash, I can't remember, about at what level does the abstraction, no longer matter, or do we actually need spiking neurons? And I think Penrose's theory is that actually, at the actual hardware at the very bottom matters a lot. I don't think that we know that yet or not. I'm a little skeptical, but
Maybe we could end with one of my favorite quotes from David Marr.
Go for it.
1980. He said that he was talking about perception, but I think it applies more generally to cognition and intelligence. He said the nature of the computations that underlie perception depends more on the problem to be solved than on the hardware that's doing the solving. And I think that Jim's beautiful work showing how similar the ventral visual pathway is that does visual pattern classification in primates is to convolutional neural networks, not designed to match those data at all, is a beautiful illustration of how very different hardwares can arrive at very similar solutions.
Awesome. All right, thank you very much for being here with us today. And I'd like to thank our panelists, Leslie Rowley and Nancy Vikash.